Am I audible,
Good
Dr.
evening,
Pankaj?
Dr. Puneet.
Good evening, good evening.
Good evening, good evening.
Am I
How are
audible?
you? Yes, you're
I'm
audible.
fine.
Okay, I think most of the participants have already joined. Okay, we'll start. Okay, before we start with the presentation, let me give a very brief intro about our expert in the second session. Dr. Puneet Kumar Jain is currently associated with the Department of Computer Science and Engineering at National Institute of Technology, Rourkela. He earned his PhD from the Indian Institute of Technology, Jodhpur, and his MTech from Delhi Technological University and his BTech from Engineering College, Bikaner. As a senior member of IEEE, he also holds the position of Vice Secretary of IEEE Rourkela subsection. Additionally, he serves as the professor in charge of the Center for Automation Technology at NIT Rourkela. Dr. Jain, areas of interest include signal and image processing, time frequency analysis, wearable healthcare. His interest is centered on digital healthcare, with a particular focus on the healthcare technology and algorithm development aimed at improving patient diagnosis, assessment, and remote healthcare. His work has been published in peer-reviewed and SCI indexed international journals and reputed conferences. Furthermore, he has contributed as a reviewer for several esteemed international journals and conferences. So, with this brief intro, I welcome Dr. Puneet Kumar Jain from NIT Rourkela. Welcome, sir.
Thank you, Dr. Pankaj, for generous introduction and giving this opportunity to interact with the participants of this event. I'm able to see a large number of participants in this meeting, around 240 or something like that. So that is an impressive number. Uh, okay, one thing can I pause my video during the presentation so that probably the network issue will not hamper the presentation?
Yeah, I think that's fine. There's no issue while stopping a video. Not an issue.
Okay, okay, yeah, fine. So first let me share my screen and let us confirm that everything is fine. Is it visible?
Yeah, it's fine. It's visible.
Okay, just let me change the slide and let us confirm that slides are being changed. So I have changed it to the first slide. Was it visible?
Yes, slide is visible, but Dr. Puneet, your voice is not very clear. It's kind of like
Okay.
fluctuating and kind of blurred.
Yeah, I think let me just stop the video. Actually, the net is not that much proper today. Is it okay now?
Please come
Otherwise, I
again.
may try with some headphone.
You can try with the headphone because the voice is not
Okay,
much clear.
just a headphone.
Yeah, sure. Take your time. Not an issue.
என்னை பார்த்துட்டு அது பாட்டுக்கு டிவியை மாட்டிட்டு தான் நிக்குது.
Dear participant, please make sure that your mics is not unmuted during the presentation. It creates a lot of disturbances for the speaker.
अच्छा
Amit
ठीक
Kumar Maurya now. It's not possible for me to mute again and again you individually. Please cooperate. And please try to interact with the expert.
Okay. Okay. So, good evening, everyone. As Dr. Pankaj have introduced that I'm going to present
on AI for smart healthcare. So, first of all, let me take an apology. There is no content slide here right now. So here, what I planned is that first of all, I will give a brief about how the artificial intelligence techniques or the machine learning techniques are shaping the current world medical intelligence. So we'll discuss few applications of ML algorithms in various domains of medical, and then I will briefly describe what we are doing at in our lab, Digital Healthcare Innovation Lab. Uh, I hope everyone now understand the area of the artificial intelligence, the difference between AI, ML, deep learning, etc. So when we talk about these words, so we are in general we talk about the rationality. So let me just briefly describe that if we are talking about the intelligence, we can describe them in the two different manner. One is the intelligence that is perceived by the human, and then there is another term that is rationality. So the difference between the two is that in its layman language, we can understand that when we are talking about the human intelligence, generally the humans are satisfiers, right? While when we talk about the rationality, we talk about the optimization. So these are the two key differences. That one talks about the satisfied results, another one talks about the optimized results. And when we deal with the machine learning techniques, most of the times we deal with the optimization. That means most of the machine learning techniques deals with computational rationality. There are lots of domains, or we can say subdomains of artificial intelligence. Many of these words and the subdomains words you might have heard. So recently, the deep learning, which is one of the subdomain of machine learning, and again, the machine learning is the domain of artificial intelligence. And in some discussions, it creates some confusion also that when we are using the words AI, ML, deep learning, are they interchangeable? So the point is, yes, somehow we can use that because the deep learning, machine learnings are the subdomains of the AI. So whenever we are using the ML or deep learning, in fact, we are using the AI only. However, is there any? Okay, I request all of you to unmute everyone until you do not have any doubt. If you want to discuss anything, you can interrupt me in between the presentation. I will be happy to discuss any topic in detail. Okay. So when we are dealing with any specific subdomain of ML and DL or any, let us say, NLP, image recognition, machine vision, etc., all are the part of the AI, and generally that's why we use the word AI. In fact, the title of this presentation is AI in healthcare, while we are not using the typical AI techniques which falls in the artificial intelligence. So we are using like some type of concepts of the deep learning, machine learning, computer vision, etc. So let's move towards the role of AI in medicine. Nowadays, AI has been explored for various applications in the medical domain. And when there are lots of applications have been mentioned in this particular presentation, these are just a snapshot of the actual scenario. We can observe that AI is being used in the medical domain, including for the disease diagnosis, drug discovery, medical image analysis, personalized treatment plans, etc. Considering the importance and the significance of AI in medical domain, various startups are coming up and they are able to raise a good amount of equities and the funding from the investors and the angel investors, etc. And this is also a glimpse that how AI is shaping the future medical field, or the importance of AI can be understood with the players which are being involved in the use of AI for the medical domain. You can observe that most of the giants of the AI or the computing world are involved in the
applications of AI in the medical era or in the medical domain. These are some applications, some popular applications for the healthcare. Although I'm not going to describe each of these applications in detail because again, these are just a glimpse of whatever the applications are available in today's market. It is just to describe that big players are coming up with various solutions which are specifically focusing on some specific application of AI in medical era. Now, when we are talking about the machine learning algorithms in the medical domain, these are certain applications which gives a clear idea that how people are using different algos, different concepts of AI for various medical applications. One of them is like the classification of a disease. So in this case, the MRI scans of the brain are being used to perform the segmentation of the lesion parts, or means the normal part versus the abnormal part, and then the diagnosis can be performed. Another area where we attach various electrodes on the maternal abdomen to analyze the activity of the fetus. So by doing this, and the monitoring of the fetus can be performed. Very popular application of AI in the medical domain was analyzing the chest X-ray images to detect the pneumonia, and it was very popular during the COVID. Very popular, another popular application of AI in the cardiovascular domain where ECG, PCG, etc. Signals are being analyzed to perform the diagnosis, to perform the monitoring, and in fact to perform the pre-stage screening of various diseases. And in fact, this is one particular domain where I'm working and will discuss a little bit in more detail how we can use these kind of signals. So there are various applications where different kind of signals, different kind of multi-domain signals, images are being acquired to analyze the functionality of different organs. So means again, these are just a snapshot that which are describing that there are lots of modalities available. Means many of us have gone through diagnosis through of these different modalities like ECG. When in fact everyone must have gone through the screening through stethoscope, right? When we approach to any particular medical doctor, he uses a stethoscope to analyze the activity of the hearts and lungs using that stethoscope by analyzing those sounds produced by those organs. So the point is by using various sensors, either it might be stethoscope or the electrodes or the medical instrument or the image instrumentations to capture the information of these organs. Then the role of machine learning comes into the picture to analyze these multimodal information to perform the diagnosis or screening. So these are now very specific applications of AI. This is one in the field of radiology, where means the radiology information or the image information can be captured for various organs. In fact, there are different image instrumentations like the CT, PET, MRI, etc. are available. X-rays is another one to capture the information of the desired particular functionality. Like if we want to analyze the veins, the blood flow of during the veins, uh, then a specific image instrumentation has to be used. If we so different image instrumentations are available to analyze different kind of functionality of each organs. Once that information is captured, the machine learning algorithms are used to to perform the diagnosis, or in fact, I will frame it in a better way to that the machine learning algorithms are being used to help the medical person to perform the diagnosis with better precision. So this is another domain where the in fact, this is one particular domain where we are also working, where we are analyzing the MRI scans of the brains to perform the diagnosis or detection of various disease. So where we have to identify the normal tissues versus abnormal tissues called lesions, might be due to the strokes or the brain hemorrhage, etc. This is another important uh, domain of the medical where AI has given us significant results. So in fact means due to the impact of AI in this particular field, it has reduced the analysis of the DNA sequences from means number of days to number of minutes. This is one more very important application. In fact, there are various tools available. Means the mobile applications are available to analyze the skin diseases, where either they are focusing either on the face skin or to detect the skin cancers, etc. In another area, respiratory sounds or the heart sounds are being analyzed. To perform the diagnosis. So this is another work where we are working, and I will discuss a little bit in more detail that how we can use these lung sounds to perform the diagnosis. There are various applications now available in the market which are based on the AI and ML algorithms which are being used in the medical domain. This is the one application which get very popular during the COVID, since the COVID screening test kits were very limitedly available at that time. So then the researchers were trying to use the X-ray images to detect the presence of the COVID symptoms, etc. Then there are various other applications. Probably I will little bit skip all these things in detail because means these are various snapshots. These are various examples where the AI is being used. Lots of research is going on in each of these domain of the medical. And the fact is that in every particular domain, the challenges are different, right? So the point is that we have to understand what are the challenges available in that particular multimodal information, and then what is the main objective of that particular information. Like in this AI in drug discovery, new drug discoveries were made with the help of the AI models. Again, so this is one more example where lots of big players are involved to use AI and ML models to perform the drug discovery. So what happened in the drug discovery is that they are trying to formulate different. Dif- they are being used to perform the pre-screening testing even without using the actual humans. So they are trying to simulate the pre-screening of the new drugs. They are able to they are using to predict the output of the clinical trials to perform the patient monitoring, etc. So lots of applications even in this particular domain are being used. Fetal monitoring, again, I think this is one example which is describing that, in fact, to analyze any specific organ, there are different modalities available. Like here, just to analyze the functionality of the fetus, lots of modalities like cardiotocography, ecography, fecal, fetal electrocardiography, fetal magnetocardiography, fetal phonocardiography are being used. So the point is that lots of different kind of sensors are being used, and all these kind of sensors provides a different perspective of that particular organ, and it depends which kind of functionality we have to analyze, and accordingly we have to select which kind of sensors we have to use. Of course, each sensor comes with their pros and cons, and according to the intended purpose, we have to select. Like, suppose if we want to perform the screening or the monitoring at home, then probably we would like to use a sensor which is unobtrusive, user friendly, and of course, means economically at a lower cost, right? While if some medical person want to use it to do accurate diagnosis or pinpoint diagnosis, then probably he or she will choose some image-based sensors. This is another applications. As I mentioned, this is one area where we are working, where we can again acquire different kind of signals and images related to the heart functionality to perform the diagnosis of various diseases related to the heart. So let us discuss about few works what we are doing at Digital Healthcare Innovations Lab at NIT Rourkela. First, let's discuss about the role of AI and ML algorithms for analysis of heart sound signals. There are few scholars and MTech students are involved in this particular area. Recently, we proposed an idea where our idea was that uh, it, the idea was based on the two-stage solution where at the user end, only the abnormality will be detected. That means the signal will be analyzed to identify is there any abnormality or not. Because uh, it's intuitive that the user should be able to understand, user should get an early notification if there is any abnormality. However, if even if he knows what kind of disease it might have, or he or she might have, still he has to communicate with the medical person. So that's how we bifurcate these two steps. One at the user end, where low cost AI/ML models will be used to perform the analysis of heart sound signals in the real life scenarios. That means few concepts of the quality assessment, denoising algorithms were being used so that these heart sound signals analysis methods are robust to real life noises. And then at the clinical end, more detailed analysis of those signals can be performed in the time frequency domain, etc., so that a better diagnosis with the precision can be performed, which the intended is to help the medical person to perform an accurate diagnosis. In this direction, which in this particular work, which was funded by Star Project, we developed an application, and I just kept this particular demonstration to give an idea that how we can construct these kind of applications, and these are there is no much rocket science when if any one of us are interested to develop these kind of applications. Uh, we just have to integrate certain concepts of AI and ML algorithms in the smartphone applications. Lots of APIs are available to do that. Only thing is that we first have to identify what kind of features we have to extract, and then what kind of low cost AI ML algorithms we have to use. Specifically, if I would like to discuss, Acha, before discussing this work, I would like to mention that at any particular moment, I just kept the brief of the recent works, what we are doing in our lab. If anyone is interested to discuss in detail specific topic, you can interrupt me during the presentation, or you can ask me at the end of the presentation. I would be happy to discuss in detail. So this is one work where we propose an algorithm to perform the denoising of heart sound signals based on a concept called discrete wavelet transform. So there are three steps: decomposition, thresholding, and reconstruction. In this architecture, in this pipeline, what we did is the modification of the thresholding method. So instead of following the traditional methods, we analyze the signals, heart sound signals, in the presence of noise, and try to analyze the relationship of different statistical parameter of this particular signal, and observe that mean, median, variance, which are normal statistical parameters, have a very specific patterns, right? If you will observe in this figure, in the the top one, where the noise is almost absent, the mean is larger than variance and median both, right? While okay, before that, I would like to mention, although that is in a very domain specific, and so instead of median 50, we use another we modified that parameter, calling it as a median 75. So that is nothing but the 75th percentile value instead of 50th percentile value. There was a specific reason. Uh, I'm not interested to discuss all those details right now. My How I figured it out, this particular talk, is that I can give an idea that what kind of works, or what how the AI and ML's algorithms can be used in medical domains, and how we are using them, right? So again, I'm not going into much detail about the technicality, that why exactly we use these parameters, etc. So means in the future slides also, I will skip the much technical details, right? So I will just give an idea that how what are the problems and how we are dealing with those problems, with what kind of ML algorithms, what kind of signal and image processing algorithms we are using to deal with them. So that's how we analyze these statistical parameters, and according to the behavior of these statistical parameters, we devise a new threshold parameter. Again, further, instead of using traditional thresholding functions, we devise another, we modified. In fact, means it was just a combination of both the soft and hard threshold function, and termed as in a mid threshold function. Then further, we optimize these algos so that the results can be optimized for the heard sound signals. Of course, it means if we have to use it for different signals, again, we have to do this optimization for that particular set of signals. So this is another work where we perform, we use the machine learning algorithms to perform the classification of heard sound signals. So uh, one thing is that generally, when we acquire these signals or images in the real world, we got these information either in the time domain or the spatial domain, right? So if you are getting 1D data, then we generally acquire this information in the time domain. When we acquire image information, generally we acquire them in the spatial domain. Now, there are lots of studies to transform these information from the time or spatial domain to other domains, like the time frequency domains and various scale domain. Uh, in the previous case, when we were discussing about discrete wavelet transform, that is another one of the example of converting the time domain information into scale time information. Similarly, this is another type of transformation technique, which stands for tunable quality wavelet transform, TQWT. Uh, so we use these kind of time frequency transformation techniques or various other transformation techniques to analyze these information, either from the signal or images, so that whatever the prominent features are available, right, in that particular information, can be extracted more meaningfully, so that the ML algorithm performance will be emphasized. Again, what kind of transformation domain we have to pick, that depends on the specific domain information, which might be diagnostically useful for that particular application. So let me give you just an example in case of heard sound signal. I think I did not put that particular example. So the point is, in case of heard sound signal, uh, if we are dealing with the heard sound signal of a normal person, there would be a particular frequency range of those heard sounds, right? While if there is a particular abnormality with that particular patient, then the frequency range of these heard sound signals will fall in a particular frequency bands. So the point is, if we can analyze the energy of these signals in particular frequency bands, then they will help to perform the diagnosis with much better accuracy, right? So if we have that information about our signal, then it is better to transform the signals from time domain to that particular sparse domain where the information is available in more sparse manner. So here in this particular pipeline, we first do some pre-processing, then we perform the decomposition and doing some denoising tasks, whatever we have done in the previous case. And then we extract the features from the time frequency and time frequency domain to perform the classification using classical machine learning techniques like SVM, KNN, ensemble methods, etc. Similar task we also repeat with a very simple deep learning method, which was using the DWT features. So I hope those who are a little bit familiar with the convolution neural network, they would be able to understand that we are just using a 1D CNN model where there were just two convolution layers. And the interesting fact, I think I did not kept those results. What I would like to emphasize here is that whatever the results we were able to achieve through these lots of steps in this particular pipeline, with this simple three steps pipeline, the results were better. So when I'm emphasizing on this, that generally the deep learning models performs better compared to the classical machine learning techniques. There is a very big drawback of these deep learning models. In medical domain specifically, and I think in every domain, uh, there is one particular requirement, and that's why people are working on that particular aspect that is called explainability of the results. So let us say if when we are applying a particular signal and the model is producing an output, let's say abnormal with category 1, right? The question is why that model is producing that particular output, right? In case of deep learning, it becomes difficult to answer that. While in case of classical machine learning techniques where we are extracting the features, since the features informations are available, they can be analyzed that in a particular output of the category, what kind what what kind of features, what were the changes in those features were there, and based on that analysis, it can be concluded that if any particular category abnormality will occur, what kind of features will change? While in case of deep learning models, it becomes difficult. So that's why people are working on various aspects of the explainability of the deep learning models. So this was just an extension of the previous work where means since in the previous work no deal with the denoising was performed in the we extended this work to perform the denoising of the signals before performing the classification so that the model would be robust to perform the analysis in the real life signals also. In a recent work, we use a technique called EQLBP. So before that, so in this particular task, we proposed two major steps. We proposed two major things. One is the quality assessment, and second is the enhanced QLBP feature. I will just briefly describe. And again, means as I mentioned that the deep learning methods generally perform better compared to the classical machine learning techniques. Still, we are interested to use the classical machine learning techniques to perform the diagnosis further. So here what we did is that yeah, here is an example. So for the quality assessment,
duration. Let's say we record it for the 20 seconds. Right? However, to perform the diagnosis or to perform the analysis of the that particular information, we need just a small chunk of that information. So let's say for the heart sound signals, analyzing the 5 cardiac cycles would be sufficient for most of the diseases, right? Or at least for to perform the detection with normal versus abnormal. So here, we just a minute. Everyone, am I audible? Anyone?
Dr. Puneet, your voice is not clear.
Okay. Should I switch the network? If it is not audible clearly, then probably I will try to switch the network.
Please do, because the voice is not clear. I think it seems like your headphones are disconnected. I don't know what's the issue at your end.
Oh,
Please.
okay. Yes, it is disconnected. Okay, I think through the headphone it was quite okay. Acha. Okay, just a minute. Uh, is it okay now?
Yeah, please go ahead.
Okay. Okay. Meanwhile, any question or any point, anyone who want to raise any point till now?
Dr. Puneet is not clear. Voice is not clear.
Just let me change the network also.
Good evening, sir. Can we use wave menu for
Yes.
applying availability?
Sorry. Can you repeat your?
For applying wavelet transform, which tool we can use?
Mhm.
Wave menu?
So you are asking about the library or means?
Yes, sir.
Okay. So means the wavelet trans. First of all, am I audible right now?
Yes, you are audible.
Okay then. Okay, fine. So since the wavelet transforms are very popular technique to perform the transformation, it is available in most of almost all tools. Like either if you are using MATLAB, Python, R. So with most of the programming languages, there would be a library which is providing you to implement or to perform the wavelet transform. Is that your question?
Uh,
Okay. Any other doubt?
Dr. Puneet, there's one question in the chat box. You can please check uh, through
In the chat box?
PCGAQ, this formula, how much error is acceptable? Hari Kumar Naidu has asked this question. Like this formula P for PCGQA, how much
Okay.
error is acceptable? This question is there in the chat
Through
box.
PCCK formula, how much error is acceptable? Okay. Okay. So the point is, let me divide this question into two parts. One thing is regarding the quality assessment, and the second thing regarding the error in the final diagnosis, right? So regarding the quality assessment, so only one thing is that if due to error, if the complete noisy part get captured, then probably the diagnosis will get affected, right? And regarding the acceptability rate, generally when we are using these machine learning techniques for medical domain, uh, our main objective is to increase the precision, right? That means the false negatives should be as low as possible. That means if we are performing the diagnosis, that is okay, somewhat okay, if any normal person is considered as an abnormal, right? In that case, what will happen? That person will go for further diagnosis. You know? But any abnormal subject should not be left away, right? That means the person is having abnormality, and the diagnosis, the pre-screening tool gives the result as a normal. In that case, that subject will not go for further diagnosis, and that would be very catastrophic for that particular subject, right? So in medical case, the false negatives are very serious concern, and accordingly we have to devise uh, the parameters of the machine learning algorithm, right? So regarding the acceptability rate, it depends. I will discuss one particular domain, the scanning of the MRI. We are only able to get the accuracy close to 80%, right, in the segmentation, and still that is significant considering the challenges in that particular field. While in case of these heart sound signals, ECG, etc., the accuracies are being achieved close to or more than 95%, right? So again, means one thing is that it depends on the challenge, the level of challenge available in that information, and instead of terming that as an acceptable accuracy, the major concern is that the false negatives should be as low as possible, right? Because that is the major concern. And as I mentioned, that whatever these machine learning algorithms are being used in the medical domain, they are being used as in a pre-diagnosis stage or the monitoring stage, right? Finally, the medical person is going to intervene, right? So the point is that these algorithms should perform the pre-diagnosis in such a way that the false negatives are as low as possible, or should be close to zero. Right? But we know that the ideal algorithms would not are not at least as of now does not exist. So that's why the people are doing further research in these domains. Fine.
Sir, one
Anything
question.
else?
Sir, one,
Yes. Yes, please. Yes, please. Please ask your question.
I would like to ask one question.
Yes.
Whether user is a physician always, user is physician always. You
So
said
I think answer, yeah. So I think the answer for this question lies in that particular slide where I kept that we are proposing it as in a two-stage solution, right? So the point is that there are multiple end users and different solutions aimed at different users, right? Like the one end user is the user itself at the home or uh, at remote areas, while another end user are the clinical persons, right? Like uh, when we are using the segmentation of MRI, the end user is the doctor itself, right? Because it does not help to the normal person to identify means where is the lesion. So there are certain applications which are built for the end user to perform the pre-diagnosis stages, while there are certain applications which aims for the medical persons.
Sir, one more question, if you don't mind.
Yes, please go ahead.
So be trained accordingly, sir. Right?
I think that's a very tricky question, because the point is that sometimes physicians have this idea, which is generally, as an engineer, we do not support that idea. Is that AI will replace the doctors, right? Probably you might also hear this particular theory. However, as of now, as I have already clarified this particular thing, I think in the initial slides, that as of now, whatever these AI and ML algorithms are into the clinical practices, they are helping out the medical persons, right? They are not trying to replace the medical persons. However, although some in certain application, in certain kind of works, automatic segmentations or the management of electronic health reports, right? Those tasks are being done more efficiently with these AI ML models compared to a human or some medical person. However, final diagnosis is still being done by the medical persons. Sorry, I think I dwelled in a different way. Can you repeat? Is that what was your exact question? Okay, yeah. So it is difficult. So okay, regarding there is one more fact is that let's say if we talk about this heart sound signal analysis, when I'm describing these things, we are focusing on the end user. That means the normal user, so that he can identify if there would be any abnormality at an early stage, right? Right now, if we would like to intend, which we are right now doing it, some work, if we have to come up with certain application which will help the medical person, that means the doctor, to perform the diagnosis with better precision. In that case, these kind of analysis, the medical person will not be interested in the final output. He will be interested that, okay, is there any extra information you can provide me about this particular signal, right? So in that case, if you might be aware, in fact, I mentioned that in case of normal subject, the frequency range of the signals will be different compared to the abnormal cases. So if the medical person or the doctor will have a clear picture of the energy in different frequency bands, he can take a better decision. And that's how these algorithms would be helpful for these doctors, for the medical persons, right? So the accurate diagnosis can be performed more quickly, right? I think we should move ahead, and then we can do more questions at a later stage. Okay. So this was regarding the quality assessment. The objective is that in the complete recorded signal, we only need a subset of the recorded signals, and we would like to get that subset which has a least amount of noise contamination, right? So again, when I'm discussing this particular technique, we are dealing with the signals recorded in the real life. That means when I'm at home, like as of now, so lots of noise are coming from outside, etc. So if we are recording these medical signals in the real life scenarios, then of course the noise will contaminate, and in that case we would like to extract only that subsequence where the noise is least present, so that the diagnosis can be performed with more accuracy. So to do that, a very simple quality assessment metric we devise, because it has to be done for every particular segment, right? So this should be a computationally efficient. Uh, these are certain examples where to demonstrate that whatever this small, very intuitive formula is describing that it is effective to identify a segment with the least contamination of the noise. After that, once the subsequence has been extracted, I will again not go into much detail about the technicality and what exactly the modification and the rationality of that modification of this particular technique. I will just give you a glimpse that how we are extracting that information. So if you will follow the first left box in this particular figure, the PCG signal first is being transformed using another transformation technique called short time Fourier transform, right? So this will give you an image where the x-axis is the time domain, x-axis is time, and the y-axis is the frequency. So we are getting a transformation in the time frequency domain, right? That means we can understand that which particular frequency content is available at what specific time. Once these spectrogram images have been obtained, we use a technique called quantum local binary pattern. These are the texture features. There were certain issues in that this QLBP in the presence of noise. So we modified certain concepts in this particular algorithm called adaptive reference pixel selection algorithm, by which we make this algorithm little bit more robust against the real life noises. So this is just an example that if there are certain corrupted pixels nearby to the center pixel, then in the conventional QLBP method, it will hamper the results significantly, while by modified RPS algorithm, stable patterns were being obtained. Just a glimpse that this particular method was able to beat various deep learning methods, various recent deep learning methods, even with a very low computational complexity. So this is one particular field. Another one is the analysis of the respiratory sounds, where another PhD scholar is working in this domain. In this area, what we do is that we acquire the sound signals through the stethoscope from the various locations from the front and back of the chest, right? And there are different categories of these lung sounds, like tracheal, bronchial, bronchovascular, vesiculars, etc. Again, in this particular domain also, the time information, that means the duration of the inspiration phase versus the expiration phase, the energy of the inspiration phase versus expiration phase, the duration between these inspiration and expiration phases. So the time information as well as the frequency information, both are very important. So again, the time frequency transformation is very critical to analyze these kind of signals, right? So, okay, this is just describing that different kind of sounds exist. Like in case of normal, there are three different categories of the normal sounds, while in case of abnormal or adventitious, there are typically six kinds of abnormal sounds exist. And these abnormal sounds relate with some various abnormalities, right? So again, our task is that first of all we perform certain denoisings, so that if the lung sounds were acquired in the real life scenarios, they can be used to perform the analysis, and then to perform the classification in these different categories. So here in this particular task, we propose an algorithm again based on the deliverability, and probably now you can correlate with this particular method with what we propose for the sound signal. However, in this case, we adopt a deep learning method to perform the thresholding. So this is again another recent work where we are using a discrete wavelet transform to perform the decomposition of the respiratory sounds. Then we are using these different detailed and approximation level coefficients to perform the thresholding, so that the denoise signal can be obtained. in this particular application, for the thresholding, the detail of that particular model is available here. What we did is that for the thresholding, we use a typical model called UNet, right? So it's an encoder decoder based architecture, where the in the encoder we perform the sequential compression of the features, while in the decoder the sequential decompression of the signals is being occurred. I would like to emphasize one thing is that the unit models are not only for the denoising, they are being used for multiple applications, and they are specifically important where the size of the input and output are same, right? So in this particular application, the input would be the noisy signal, the output would be the denoise signal, but the the size of these both signals will be same, and that's why we pick the unit model. Uh, okay, again, I'm not sure that how much this particular information was useful, but at any moment, if any one of you is interested to discuss this particular technique in detail, I would like to suggest, I will share these slides with all of you. I will share these slides with Dr. Pankaj and will request him to communicate these slides with all of you. Uh, First of all, you can follow these references, and at any moment, if you have any doubt in this particular technique, I will be happy to discuss in detail. Okay, so this is one of the recent work we work in the domain of the sound denoising. We also work recently. We have also one accepted work on the land sound classification, but I could not keep that particular work in this presentation, where we are using some knowledge distillation techniques. Okay, let's move to the next one. Okay, we have 30 minutes. Fine. So this is another work, very interesting domain where there are certain students working in this domain. I hope everyone is familiar with the term ECG. Many of you might have gone through the screening through the ECG, right, which stands for electrocardiography. Typically, in the electrocardiography, multiple electrodes are being placed around the chest. The objective is to analyze the electrical activity of the heart from different angles, right? So if you will analyze the right part of this particular figure, you will observe that we are placing different electrodes, and uh, just to measure the movement of the electrical conductions, the electrical impulses being generated at different part of the heart and moving from in different directions. We are analyzing in each directions through multiple electrodes, right? Again, now different kinds of challenges are being posed in different data sets, like how with how much accuracy we can perform a particular diagnosis. Should we use 12 leads? That means typically we use the 9 electrodes to analyze the complete electrical activity of the heart. Should we use all those 12 leads? Can we do it with just 3 leads? Can we do it just single leads, etc.? So different problems with different objectives are being posed even in this particular domain. I I missed one particular aspect in this particular talk, is that I should keep the details of various data sets, various prominent data sets available in these domains. So again, I will request to all the participants that those who are interested to know little bit more detail about any specific topic regarding the data set, regarding the technique, I will be happy to help. Okay. So in this particular task, what we are doing is that I hope everyone might have encountered that in the tier 2, tier 3 cities where the cardiologists are not available, the ECG machines are being used to record the electrical activity of the heart. The ECG report is being generated on the paper, right? We are calling that ECG report. But the point is that this is there is no cardiologist available to analyze this ECG report until that particular patient is referred to tier 1 city, right? In fact, in the tier 1 city, the number of cardiologists are limitedly available. Fine. So, due to this scarcity, most of the times, in fact, a very popular heart disease, which is called heart attack in the layman language, the biological term is the myocardial infarction, right? That goes untreated, or sometimes it takes longer time to get identified, right? Due to that, many times the situation get worsened. So the objective of this task is that once this ECG paper is generated, we have the smartphone. Most of the means in even in the tier 2, tier 3 cities, the persons have the smartphones. The image can be captured through that smartphone. This image, now there are the two possibilities. This captured image directly can be used to perform the diagnosis, right? Although this particular approach will be little bit more complex, because analyzing an image have a large amount of information, and again the storing of this information, transformation of this information again takes a more cost to the system. So what we are trying to do is here is that we are now this image will be converted into 1D signals. So as I mentioned that generally the 12 lead signals are being acquired. So that means through this image, the 12 1D signals will be reconstructed, right? Once this 1D information has been reconstructed, then the low-cost machine learning techniques can be developed to perform the diagnosis even at the smartphone level, right? So this is the objective of this particular task, where again we have developed certain algorithms, although they are in the communication, and that's why I have not kept, yeah, I have not kept those techniques. But again, we can discuss little bit more detail in our personal communications. But it's let me emphasize one important point on this particular task is that there is one very popular platform in the medical domain. Those who are interested, or those who are working in the medical area, might have heard the term PhysioNet, right? They pose various challenges in the medical domain. They also provide the data set, and this particular problem, digitalization of ECG signal, was posed in 2024 only. So this is a recent challenge where the researchers are working. So let me move to another domain where we are working. That is regarding the image analysis, or specifically the analysis of the brain MRI images. MRI stands for magnetic resonance imaging. As I mentioned in the earlier slide, that there are lots of image instrumentations to analyze the functionality of any specific organ, like MRI, X-ray, PET, fMRI, CET, etc. Right? Each of these image instrumentations or the modalities provide a different perspective of that particular organ. Like if we are talking about the MRI, MRI provide the information about the tissues or the soft tissues specifically. While if we talk about the X-ray, they provide the information about the density, right? So So it depends on what is the objective, what is the purpose, or what kind of the what are the symptoms by which the
Dr. Puneet,
medical person takes a
Dr. Puneet,
decision that
sorry to
what kind
interrupt
of,
you, but
yes,
your PPT is not visible actually.
okay,
Contents are
I
unshared by
get
mistake or
disconnected.
somehow. I don't know.
Okay, let me restart. Yes, it is that. Is it visible now?
No, sir.
Yes, now it's visible. Okay, dear participants,
So
it's a
No,
when
request.
it was get disconnected,
Dr. Puneet, just
no, it is not.
dear participants, please don't write present here in the chat box. Please, for attendance. Attendance is to be marked through Excel sheet only. We can discuss it about later on after the presentation. Don't write present in the chat box. Sorry, Dr. Puneet, please continue.
Okay, fine. I think the slides are visible now.
Yes, now slides are visible and your voice is also clear. Please go ahead.
Okay, fine. So, should I continue from this, or have we skipped the previous slides?
Nani, please continue because I interrupted just on this slide only.
Okay, okay, good. Fine, fine.
Your voice is clear,
Okay.
not an issue.
Okay,
That time.
great. So, in this particular application, we are using the brain MRI images because our objective is to identify abnormal tissues, right? And they are called as lesions. These lesions may occur either due to the strokes or hemorrhages, etc. Right? Yeah, this is one example where different modalities are given like MRI, CT, MRA, CTA, etc. And you should be able to observe like in different modalities, different information or different perspective of that particular organ is available. In fact, in the MRI, if we have to observe, if we want to observe a very specific kind of tissues, then we can again modify the certain parameters of that image instrumentations, right? So then again, different modalities in MRI itself are there, like FLAIR, DWI, T1W or T1 weighted images, T2W weighted images, etc. The mask is nothing but the ground truth. That means in this particular example, this particular part is abnormal tissue, right? So let us assume the objective is that these kind of images are given. Machine learning model should be able to identify where is the lesion, but what is the actual size of the lesion, right? Yeah, for this, at least for this particular application, the data sets, the prominent data sets I have kept here. So means the recent ones. There are two recent data sets. One is called ISLES, and another one is Atlas. For this, the tumor, there is another data set called BREDS is also available. Right. So here we are focusing on the stroke. There are certain challenges in this particular domain, like intra-class inconsistency, inter-class indistinction. That means the normal lesions appear as an abnormal lesions, while the abnormal lesions appears as the normal lesion. Then the boundaries are very irregular and fuzzy. That means there is no sudden change in the boundaries from normal to abnormal and vice versa. Furthermore, the locations are also very distracted sometimes at multiple locations. Like if you are able to observe in case of slice 4, the lesion is very distracted and at a very multiple locations. So that's how it becomes very challenging. And some of you ask regarding the accuracy, and in this particular application, even it is difficult to achieve an accuracy of close to 80%, right? That means if the lesions are being detected with an accuracy of 80% only, right? And that is considered a significant one. So that depends on the challenge available in that particular information, right? Regarding the acceptability, again, when we are talking about this particular task, uh, as of now, means difficult to comment what will happen after 5 or 10 years. As of now, whatever being is done is being performed to help the radiologist, right? So this is another application of the unit. I hope you might resemble that we are using the unit model in various other applications. One of them was the denoising of the heart and lung sounds, right? In this particular task, the point is that the unit itself is not significant, is not sufficient to perform the segmentation of the lesions. So we have to use certain attention mechanism. So in the layman term, if I explain what mean by the attention is that our human brains are very much accurate in the attention mechanism. What mean by that? Suppose if we are looking on a particular image and if we are interested in a particular object, in that particular image, then our brain is very much accurate to put our attention on that particular object completely, right? But it will discard other information. That means even if there are certain changes in other objects, our brain would not be able to distinguish those information or those changes, right? So this is an attention. In case of deep learning, in case of machine learning models, similarly, people are trying to incorporate certain attention mechanisms by which model becomes efficient, or model becomes capable to put more focus on those areas which are more important to perform the diagnosis, or where the abnormal tissues are available, right? And lots of attention mechanisms are uh, means have been, I will use the word explorer, because uh, means after 2018, when the triplet CBAM squeeze excitation modules came into the picture for the attention, people started using these techniques. And I hope you might have heard the term called transformer, right? So transformer is nothing but one kind of attention mechanism, right? That is called self attention. So here we are, means again in this particular domain, we are working on, we are coming up with different attention mechanisms which help these unit models, or specifically the convolution layers, to focus on the diagnostically important part of the MRI image. Okay, I did not put much detail about what kind of attention, how actually we are modifying those attention mechanisms to work on this particular thing, because again, means for the whatever the domain I have discussed earlier, we are also using the attention mechanism. But again, depending on what kind of information would be more meaningful for that particular application, accordingly the attention mechanism has to be modified, right? So that's why I did not keep that detail here. I would like to just emphasize on this particular part is that uh, most of the recent deep learning models are coming up with certain kind of attention mechanisms, right? Because these attention mechanisms improve the accuracy of the deep learning models, as well as sometimes helps to reduce the complexity of these models also, right? Because even with the smaller model, with the help of attention, the accuracy of these models are significant. So this is just a snapshot of the results of various techniques, existing techniques. I hope no proposed one right now. Yeah, okay. So this is just an idea that what kind of output of these models would be there. This is describing the green part is as in the true positive. That means where where the lesion was there, detected as a lesion. False negative, that means the lesion was there but detected as normal, and which is the most concerning issue, right? As I mentioned, in case of medical field, the false negative should be as low as possible. And the false positive, that means the normal tissue is termed as an abnormal tissue. I think this is the last domain where one of, I think, yeah, the two of my students are working, where the objective is to perform the classification of these blood cells, right? So in a typical human blood, there are red blood cells, white blood cells, and then around 75% is the platelets, right? In the white blood cells, there are two categories, granulocytes and agranulocytes, which are further divided into subcategories. So in total, there are five white blood cells. Each of these white blood cells plays a very important role in the human body uh, to detect the infection, to deal with the infections, etc. Right? So based on if anyone of I hope many of you have gone through the CBC analysis, the complete blood cell analysis, and if you will observe that particular report, you will identify that the number of each of these components, right, the number of neutrophils, basophils, eosinophils, etc., will be mentioned, right? So the number of occurrences of these specific blood cells indicate that is there any infection or is there any abnormality is there or not, right? So in this particular task, we want to identify, we want to classify these cells and then to perform the counting of these cells so that the diagnosis can be performed. For this, we use a different kind of model called YOLO. Stands for you only look once, right? So a very popular model to perform the object detection. Although means this is a little bit older version of the YOLO. I think recent one is the YOLO 12, and so here again means what we focus, there were three changes. Importantly, the main change was the introduction of the attention mechanism. So we construct a new architecture called C3TR, where the transformer block was integrated into the convolution layers, and this C3TR structure was used in the backbone of the YOLO V8. Further, multiple heads were added, and uh, the neck was updated to focus on small size white blood cells, right? So I hope, yeah, this is the end of this particular talk. At the end, I would like to conclude that first of all, AI and ML models are uh, impacting the medical field in various aspects, including the diagnosis, including the new discoveries, including the early stage diagnosis, reducing the burden on the medical experts, etc. Right? And another fact is that they are empowering smarter care. So this is the conclusion that AI is not here to replace the healthcare professionals. Although in certain cases, like in case of let's say the radiologists, in certain applications, probably the AI and ML models in the coming future may replace those jobs. But at the end, the medical person intervention would be required. But because at the end, uh, when once even the diagnosis has been performed with these with the help of these models, right? The actual treatment, what kind of treatment has to be performed, that has to be done by the medical experts. So the theory is, as of now, is that AI is not here to replace healthcare professionals. It is here to empower them, right? It is here to empower the medical expert. It is here to empower the end users in the remote areas, in the rural areas, and that is our objective. So by this, I would like to end this particular presentation. And now, anyone, if have any doubt or want to discuss any topic in detail, I will be free to do that. And I think I have already mentioned, I will share these slides with Dr. Pankaj, which will be shared with all of you. So my mail ID is available here. You can contact me through this mail ID at any particular moment. Having just a request that in the subject, just put the name FDP, let's say FDP NIT Kurukshetra. So I will not miss that particular name. Yeah. So now the meeting is open for the questions, please.
So
May I-
anyone from the participants want to ask anything, want to discuss any point, you're welcome, participants.
One small question is there.
Yeah, sure.
Yes,
Please.
please.
Actually, sir, whenever we talk about any particular, it is a very vast area basically we are talking about, and applications are very many applications are there. So, suppose we are talking about the voice, you are denoising, what? So, any age factor is going to impact that result? Any like if 70-year person is there or a 16-year person, so is there anything like that, like
Yeah.
we have to
Yeah.
data set?
It's a very good question because Of course, means not only the age, in fact, the genders, in fact, the geographical locations. Each of these parameters impact the characteristics of the signals and images. So let's say, in case of heart sound signal, uh, for the heart sound signal of the children's, the, the features will be completely different compared to the adult heart sound, right? The frequency range of the children heart sounds, or the pediatric heart sounds will be very high compared to adult heart sound, right? Similarly, for the elder age people, the heart rate as well as the frequency components will be different compared to adult one, right? Uh, and so this is one factor, right? Similarly, geographical also. The characteristics of these components, let's say for the Indian population, would be different compared to the population for another country, right? So there are various factors which affects, which, or we can say that uh, a medical expert takes a lot of factors in consideration when he or she takes the decision, right? And that's why it becomes difficult for an AI ML model to perform the final diagnosis, right? So,
Okay,
okay,
sir.
regarding this, one thing is that the generalization capability, this is the word we use for the AI ML model, the generalizability. That depends what kind of the diversity of the signals are available in your data set. And in most of the domains, right, means when we are using different domains, means various data sets from different domains, in most of the data sets the diversity is very limited. They either generally focus on certain geographical location, they either focus on very specific category of the disease, or let me give you an example regarding the heart sound signal, right? Uh, uh, the most popular data set comes from the Physionet only, right? Where there are in the example what I have kept in that particular quality assessment, there are around 3,265 number of samples, right? In that number, hardly 50% are from the female candidates, right? And when we conducted the experiments in our lab, right, on the normal subjects, we observed that the frequency range of heart sound signals of a male compared to female are different. That means whatever we are developing, right, as of now, would not be much meaningful for the female patients. Did you get it? So yes, it's a big questionable that whatever we are developing based on the given data sets, they have very limited application as of now.
Thank you, sir.
Okay, Dr. Puneet, there is one question in the text as well in chat
Okay.
box. What is the difference between PET scan image and normal CT scan image?
Okay, so CT scan is kind of a 3D X-ray, right? While PET scan is the positron emission transmission. So in that case, the molecules are being studied, right? So again, as I mentioned, that different instruments are available. Like in case of magnetic resonance imaging, right? Uh, the point is they focus on different minutes of those particular organs, right? Like in his name is suggesting positron emission.
Tomography, I
So
think.
I forget about the tree. So
Tomography,
means
tomography.
it's,
It is
yeah, tomography, yeah, positron emission tomography. So in this case, the movement of the positrons are being analyzed. That means, uh, so in every organ there are different molecules, there are different cells, and each cells have different density of the positrons, right? So when we analyze these positrons, if there would be any change in those cells, the positrons will change, right? So the behavior of these positrons, right, will be analyzed in the PET. While in case of CT, the density of the cells or density of the muscles, the density of the bones are being analyzed, right? So different image instrumentations provide different perspective of each organ, right? Similarly, the MRI is again a different one.
Another simple difference is I think CT scan is normally black and white and this PET scan is colored, isn't it? I don't
Yeah,
have. I'm not
yes,
expert of
yes.
this field, but somewhat I think.
Yes, it is quite true because CT is nothing but let's say you are having an X-ray machine, but now you are rotating this X-ray machine to
3D
take the
X-ray.
pictures in the 3D domain,
Right, right, right.
right? So that's how the CTs are being constructed.
Right. Another question from Kavinder Singh. Will these IoT-based apps may replace the doctors in near future, like China is doing? I think this point, I think Dr. Puneet, you have discussed, isn't it?
I think I have emphasized a lot on this particular aspect because there is
Right.
a very hot debate on this particular topic that will the AI replace the medical experts? As of my understanding, the answer is no as of now. Only thing is that what I support is that in for few tasks, AI ML model will replace, but as a medical expert, as a medical doctor, difficult at this stage to say yes or no.
Because diseases even keep on evolving, so you need new images, and that diagnosis is to be done by doctor only.
Uh,
So,
uh,
right,
to answer that question, I think one thing is that I mentioned that the symptoms or the characteristics of these signals and images vary from gender to gender, geographical locations, etc. Let me give you an example. There is one relative, and her parameters, her vital parameters are such a way that if an unknown doctor will analyze, he that doctor will say she is in a very critical stage, right? But the doctor who is performing means the regular analysis of that particular person, he understands that he is quite normal for that. He is quite normal. So the point is that there are certain parameters, there are certain conditions where those parameters might be abnormal for someone, but for someone that is working as a normal. So medical person has to understand various aspects while taking his diagnosis decision.
right, right, right. Okay, any other questions, or should we end this session? What is EEG? Sir, another question.
What is EEG? EEG stands for electroencephalography, and again means we are putting electrodes to measure the electrical activity of the brain, right? So in general, it is non-intrusive. That means we generally do not place the electrodes inside the skull. However, there is an intrusive version of the EEG also, like if you might have heard the chip by the Elon Musk company, right? So that domain is also being explored, but when we talk about the electroencephalography or EEG, that is typically an intrusive one where the electrodes are placed on the skull to analyze the electrical activity of the brain, right? And again, means how many electrodes, what should be the location of those electrodes, right? That depends what is the objective. I hope those who are the person who is asked this question might have understand that there are different regions of the brain which have been understood by the scientists that there are frontal lobes, occipital lobes, parietal lobes, and each region of these brains are responsible for each different functionality, right? So in fact, you might have uh, there was one experiment that let's say if for someone someone's hands get paralyzed, right? So that means this brain is not able to generate the signals so that the hand can move, right? So in that experiment what they did is that they recorded the signals, the EEG signals of a normal person. He is giving the command to move his hand, those electrical signals being transferred to this paralyzed person, and the hand of that paralyzed person get moved, right? That means, as of now, although not with much detail, the study of the brain has been clearly explained, but significant development has been done in the field of the brain to understand that how the neurons actually works in the brain to perform a particular functionality, right? So that field is electroencephalography.
I think it's done. No more questions. Thank you, Dr. Puneet, for such a wonderful session. Your participants are even praising you in the chat box. Excellent session, super session. So thank you so much, and they loved your session, sir.
Okay,
Okay,
thank you, Dr. Pankaj. Only one request. I will share these slides with you. Please share with the audience. So at any later stage, if they have any question, they can discuss with me.
yeah. Definitely. I'll share at the end of the course. I'll share it. I'll collect all the PPTs from all the experts and then share with them.
Okay, great. Yeah.
Okay, dear participants, thank you, Dr. Puneet. You can leave. I have to give them a message. So I'm here.
Okay,
Thank you
okay.
so much.
Yeah, thank you.
Okay, dear participants, there's one information. Don't worry about the attendance. What we can do, we will float a Google form tomorrow for tomorrow's session as well as today's session. So you can mark your attendance for today and tomorrow collectively tomorrow. Is it fine? And please,
Yes,
it's
sir.
a request. Don't type good evening, anything unnecessary in the chat box. Otherwise, some questions can be mixed. Definitely, you can give your feedback in the chat box after the completion of the session. It's not an issue. But someone's important message should not be missed. This is just a request. Okay, thank you everyone. Good night.
Good night, sir.
Good night, sir.
Good night, sir.
Good night, sir.